Hello everyone, I would like to introduce myself. My name is Loureiroeg. This work that I am presenting is entitled Mixed Mode Fracture Toughness of a Structural Adhesive by the Single Leg Bending Test, and I would like also to acknowledge the help of my colleagues Fernando Loureiroeg and Ricardo Rocha, which helped in this work. Here we have the framework of the presentation. We will begin by presenting the objectives, then a short introduction on the characterization of adhesive body joints, a small description of the SLB test, and of the JIIC method. In the development, we will address the experimental and numerical work, the JIIC method for parameter estimation, the correlation between the experimental and numerical data, and finally the determination of the fracture energies G1 and G2 in tension and shear, and the cohesive strengths Tn0 and Ts0 in tension and shear. The fractural analysis follows, beginning with the R curves, the fracture envelopes, and finally the cohesive loss. In the end, we will draw some conclusions about this work. Regarding the objectives of this work, we want to assess the fracture properties of adhesive layers under mixed mode conditions, considering that we have three different adhesives, a brittle one, a moderately ductile, and a ductile adhesive. We are going to consider the single leg bending geometry to perform this study, and we are going to use the JIIC method as the data reduction method to obtain the parameters of the adhesives. Regarding the fracture analysis, as I said, we are going to consider the R curves, the fracture envelopes, and the cohesive loss. To begin with a short introduction on the adhesively bonded joint characterization. The adherents were made of a composite material, in this case a non-directional carbon epoxy prepreg, and three different adhesives. The Araldite V138 is a brittle adhesive. The 2015 it already has some ductility, around 5%, as we can see in the figure to the right and below. And finally the JIIC 47752 is the most ductile of the three adhesives that we are testing here. In this figure we can see the single leg bending test geometry, which is suitable for mixed mode conditions, although it has a higher preponderance for mode 1, and it has an initial crack length A0, which is defined during the manufacturing process of the specimen. In this figure we can see all the geometric variables that are relevant to the specimen, and we can see that this is also a 3-point bending test in which one of the adherents is shorter than the other, thus creating a mixed mode loading. We are going to test two formulations. One is the Williams formulation, but we are going to focus with a higher preponderance in the JIIC formulation, which is a J-integral formulation, which allows us to obtain G1 and G2 as a function of the tensile and shear openings of the crack, and then to obtain the cohesive loss by differentiation. As I said, we can obtain the cohesive loss, the sigma W curve, which is the tensile cohesive law, by differentiation of the G1 W0 curve, and the shear cohesive law, which is the tau delta curve, which is obtained by the differentiation of the G2 delta 0 curve, thus, as I said, allowing us to obtain the shear cohesive law. Regarding the development of this work, we begin by showing the experimental load displacement curves for the three adhesives. We tested 7 specimens for each adhesive, and as you can see we have a good correlation between specimens between each adhesive, which is always an important feature to mention. Regarding the numerical work, we performed numerical models of the SLB tests such that we could extract 3 relevant parameters to obtain the G1 and G2 and also the cohesive loss in tension and shear, and these 3 parameters are the relative rotation between the 2 beams at the loading line, theta p, the local separation at the crack tip in tension, W0, and the local separation in shear at the crack tip delta 0. Regarding these parameters, beginning with theta p, we obtain this parameter by calculating the angle between two vectors, the vectors EF and GH, which gives us the rotation between the upper and lower adherents. Regarding the normal or the tensile separation, we considered the perpendicular distance to a tangent to the line A dot, such that we obtain W0, and then this W0 is the opening minus the adhesive thickness. Finally, we have a very similar formulation to obtain delta 0, which is given in this graphic by the perpendicular to the A dot line regarding to the point B, thus giving us the shear displacement the crack tip. Here is a summary of the formulation that we are going to use, the JIIC formulation. We have G1 and G2 as a function of the normal and shear openings. We are going to use all of this data to formulate the J integral, and from this formulation we are going to obtain G1, G2 and the cohesive stresses Tn0 and Ts0, which all of this information together will give us the R curves, the fracture envelopes and the cohesive laws. Regarding the fracture analysis and beginning by the R curves, here we have an example for one specimen of the tensile and shear R curves. We have here the JIIC method and also the Williams method. We can see that the crack length initiates from A0, which is predefined by the specimen manufacturing, and we have an horizontal baseline that tells us that we have a stable crack propagation. We can also compare the two methods, and we can see that the mode 2 agrees perfectly well, although in terms in mode 1 the JIIC formulation presents slightly higher values. Here we have the corresponding curves for the other two adhesives, the 2015 and the 7752, also allowing us to making the comparison between the two formulations. Regarding the fracture envelope, this is a very important feature for the crack propagation analysis in structures, because we usually have mixed mode crack propagation. In this graphic we have 4 curves corresponding to 4 exponents in the power law mixed mode criterion, the parameter alpha, and we plotted here the different points for each adhesive of G1 and G2, and we can see that the most suitable exponent for this adhesive is undoubtedly the exponent of 0.5, which is on top of the values obtained experimentally. Here we can see the fracture envelopes for the other two adhesives. We can see that for the 2015 the experimental points are closer to the alpha equals to 0.5, although it does not overlap them completely. And for the polyurethane adhesive we have a completely different behavior, as the experimental points are close to the alpha equals to exponent. After having the fracture envelopes, the next step was to obtain the tensile and shear cohesive laws of the adhesives by differentiation of the G1 and G2 as a function of the openings of the crack in tension and shear, and we have here the results obtained for the brittle AV138. We can see that we have some scatter between each curve of each adhesive, but we have a good agreement in the maximum stresses and also the fracture energy, which is the area and under the cohesive laws. We performed a similar procedure for the 2015 and 7752, and we can see that we have also a good agreement, but here we have to emphasize that the 7752 has a different shape than the other adhesives because of its ductility, so it has a higher steady state value opposed to just a peak value, as we can see in the other two adhesives. Here we have an overall view of the results obtained, the average G1 and G2 for the three adhesives, the average maximum load and the maximum load displacement of the P-delta curves, and the average cohesive strengths in tension and shear. We can see that regarding the toughness, the Sika force is the best, while regarding the strengths, the brittle AV138 has clearly the higher strength between the three adhesives. And we can also see that we have some scatter, but the results are good. And finally, we draw some conclusions regarding this work. We can say that based on the results that we present here, the J-integral method is a solid approach to obtain the G1 and G2 of adhesive joints in mixed mode for different adhesives. We tested two different formulations, the formulation of G and Williams. The J-integral formulation is a valid approach, and since it is based on the J-integral, it also allows to obtain the cohesive laws, which is a major advantage if you want to make strength prediction based on cohesive zone modeling, for instance. And we say that the parameters estimation required for the J-integral proved to be a good alternative to using mechanical and optical sensors, which have to be used if we want to have the real parameters. Thank you very much for your attention. I hope you like the presentation.